Hey everyone, let's dive right into this explainer. We're going to completely shift your perspective on math today. We are moving away from blind formula memorization, and instead we're going to build a highly visual, logical toolkit. If you're ready to see calculus in a whole new light, you are definitely in the right place. Look, if you've ever felt totally intimidated by higher level math, or if you've looked at calculus as just this endless, grueling list of meaningless formulas you have to cram into your head before a test, you are absolutely not alone. It's a super common frustration. But here's the thing, it usually just stems from using the wrong tools for the job. To fix that, we're introducing something called the logical algorithmic method. Think of this as a literal superpower cheat code. It completely transforms math into a sequence of easy, highly visual steps. By breaking these massive, complex problems down into discrete, deterministic actions, we completely eliminate the guesswork. We're talking about building actual constructive thinking here, not just plugging in numbers. So here's our logical roadmap for today. We've got 1. The algorithmic math toolkit. 2. Transforming graphs without calculators. 3. Step-by-step function analysis. 4. Reading derivatives visually. And 5. Demystifying the plus C. Let's get into it. Starting right off with Section 1, the Algorithmic Math Toolkit. Now, according to research from the UCL Further Math Support Program, students' math toolkits are often pretty severely lacking. Why? Because they rely way too much on algebra. Like, algebra is treated as the beginning and the absolute end of problem solving. But to truly grasp these concepts, we need to expand. We have to add diagrammatic and visual tools to our arsenal. We literally need to see the math.
Which brings us nicely to Section 2, Transforming Graphs Without Calculators.
Did you know you can sketch completely complex functions without plotting endless data points on a calculator? You really can, just by applying logical transformations. We're talking about parallel shifts along your axes, visually stretching or compressing the graph, reflecting shapes across the coordinate axes, or even folding the graph using absolute value functions. And a pro tip here, using contrasting colors on a whiteboard to track your step-by-step changes makes the whole process incredibly intuitive. By actively comparing that standard algebraic equation to the visual, geometric view, you instantly stop guessing. You actually start reading the graph's behavior, almost like a story. A minus sign? Well, it isn't just a symbol on a page anymore. It becomes a physical command to shift or reflect your shape in a real space. Moving on to Section 3, Step-by-Step Function Analysis. Following this exact algorithmic checklist is going to give you massive problem-solving power. Step 1, identify the domain and plot your discontinuities. You know, especially those infinite ones. Step 2, plot your zeros and intercepts, so you find exactly where the function crosses the axes. And Step 3, find your vertical and horizontal asymptotes. Just doing this gives you the core qualitative behavior of the entire graph. Just look at this. Notice how plotting those initial endpoints, adding your dashed asymptotes, and just marking a critical point instantly generates a nearly complete skeleton of what is otherwise a complex logarithmic function. The rest of the graph? It's really just logically connecting the dots based on where the function naturally has to go. Okay, let's step it up. Section 4, reading derivatives visually. Focus in on these two curves for a second. The first derivative actually acts as our compass. It shows us exactly where the function changes direction, like where it decreases down into a valley or increases up to a peak. And the best part is, we don't need a massive, intimidating wall of text to understand this. We can just visually locate exactly where the slope hits zero. But wait, we can go even deeper. While the first derivative points out those critical points, the peaks and valleys, the second derivative acts like a topographical contour map. It reveals these clear arcs of convexity, concavity, and those sneaky hidden points of inflection, where the curve basically wiggles and changes its structural shape. This clean little rubric synthesizes the second derivative test beautifully. It shows you how a simple positive or negative sign in the second derivative geometrically guarantees a minimum or a maximum. A positive second derivative? It means the curve is concave up, kind of like a smile, which confirms a minimum. A negative second derivative? That means it's concave down, like a frown, confirming a maximum. Simple, right? So, by applying our visual algorithm, you can look at a stack of unlabeled graphs like this and logically deduce which is the original function, which is the first derivative, and which is the second. How? Literally just by checking the zero crossings. Think about it. Where one graph hits a peak, its derivative absolutely must cross that zero line. It takes a scary calculus problem and turns it into a really fun, simple matching puzzle. And finally, Section 5,
demystifying the plus C.
All right, the absolutely crucial point here is that integration is just the inverse of differentiation. That means we can look at a gradient function, like the dashed line you're seeing here, as a purely geometric object. We are literally just tracking the slope of the tangent as it surfs along the main curve.
When we do these visual derivative puzzles, connecting, say, a cubic function to its quadratic gradient, we realize something kind of profound. We are actually doing integration without using any algebra at all. We're just working backward from the gradient to rebuild the original curve. Mind-blowing, right?
And here is the incredible aha reveal. Notice how integrating a gradient function creates an entire family of parallel curves? The only thing that's different about them is their vertical translation on the y-axis. Because shifting a graph up or down doesn't actually change its slope. Literally any of these parallel curves could be the answer. This visually proves exactly why we have to add that elusive plus C constant. It completely accounts for that unknown vertical shift. As the research states, using multiple representations makes mathematics way more exciting. By replacing rote memorization with this diagrammatic, step-by-step logic, math totally transforms from a frustrating chore into an exciting, perfectly connected puzzle. You're no longer just crunching numbers in the dark. You're actually decoding a visual language. Once you realize you have this logical, algorithmic superpower, it changes everything about how you approach problems. So I'll leave you with this. What other abstract concepts are out there just waiting for you to visually decode them? Thanks for joining me on this explainer today, and keep looking at the bigger picture.